Okay, today we're going to look at finding area between curves. So to represent this, basically right now, for integrals, we've just found the area under one curve in the x-axis. Now we're going to have two functions. So this purple function is be my f of x, and I'll let this green function be g of x. And let's say I want to find the area between f of x and g of x from x equals a to x equals b. And so the area I'm trying to find is this following shaded region. Given that f and g of x are continuous functions on the closed interval from a to b, and g of x is always below f of x or equal to f of x, then the area bounded by the graphs of f and g of x and the vertical lines x equals a and x equals b is found by following the following equation. Area is equal to the integral from a to b, beginning and the ending of our interval. And then I want to find the height of this representative rectangle I just drew in red. And so the height of that representative rectangle is going to be the height of my function f of x minus my height at g of x. And that'll represent the height of that representative rectangle. And then I need to times that by the width of my rectangle, which is my change in x, which is dx. And then integrating that. So a better way to remember this is the integral from a to b of the top curve minus the bottom curve, dx, is the area between two curves. So that's our basic formula we're going to be using in most of this section. So let's do our first example. Let's find the area of the region bounded by the graph of y equals x squared plus 2 and y is equal to negative x from x equals 0 to x equals 1. What I want you to do first is always kind of do a quick sketch of these. Now notice I'm not doing a perfect graph. I'm just doing the basic shapes. I know that this is a parabola up 2, and then I have the line y equals negative x. So the line through these two, and then I have from x equals 0 to x equals 1, and then shade in the area you're going to find. So my shaded region is this, and then draw your representative rectangle. And so here's my representative rectangle. So my area is going to be equal to the integral from 0 to 1, beginning to the ending of my interval, of my top curve, which is x squared plus 2, minus my bottom curve, which is negative x, dx. And that's it. So now I'm just going to simplify before I integrate, and I get x squared plus x plus 2 dx. And then it just integrate it like normal. And I get 1/3 x cubed plus 1/2 x squared plus 2x evaluated from 0 to 1. So plugging in 1 in place of every x, I end up with 1/3 plus 1/2 plus 2 minus, replacing every x with 0, this ends up being 0. So now I just need to figure out what 1/3 plus 1/2 plus 2 is. And I get 17/6. So the area between these two curves from x equals 0 to x equals 1 is 17/6. All right, you try this next one. Okay, again, start by drawing a quick sketch of this curve. So the curve y equals x, e to the x is here. And then the line y equals x. And we're going to go again from x equals 0 to x equals 1. So this is the area we're trying to find. And so I'm going to draw my representative rectangle. And so my integral is going to be from 0 to 1 of my top curve, e to the x, minus my bottom curve, x, evaluated at dx. All right, so integral of e to the x is e to the x. Integral of x is 1/2 x squared, evaluated from 0 to 1, replacing every x with 1. I get e minus 1/2, replacing every x with 0 is 1, because remember, e to the 0 is 1. So my answer is just e minus 3/2. Okay, so this is the most basic form of finding area between two curves. Now, what we're going to do is sometimes the area between curves, the curves actually intersect each other, because notice none of these curves intersect each other, because by our formula, the functions can be equal to or less than. So what I'm going to do is, again, I'm going to start this problem the same way, and I'm going to start by sketching my graph. And make sure when you're sketching these graphs, you clearly label each curve. So this is my parabola. Now I'm going to graph the line y equals x. Now this time I didn't say between given x values. You have to find the x values in which you're finding the area. So if I'm finding the area between the two curves, this is the area I'm looking for. So my first step this time is going to be to find the x value where my shaded region begins and the x value where my shaded region ends, which would be these two dots. To find this area, all you do is notice that this is where the blue line intersects the green line. So this is found by setting your two functions equal to each other. So in this case, I'll have 2 minus x squared is equal to x. And then this is quadratic, so I need to get equal to 0. And then I can factor this quadratic. And I find that my solution to when f of x equals g of x is at -2 and +1. So my interval is going to start at x equals -2 and go to x equals 1. So I'm going to integrate from -2 to 1. Then I look at my representative rectangle. The curve on top is the blue curve, which is 2 minus x squared, minus the curve on bottom, which is the green curve, which is just x. Simplifying that down before I evaluate, I get -x squared minus x plus 2. Then let's integrate this and evaluate this definite integral. Replacing every x with 1, I just end up with -1/3 minus 1/2 plus 2. And then replacing every x with -2, I end up with 8/3 minus 2 minus 4. Now let's simplify each of these parentheses groupings down. And my result is 9/2. So the area between these two curves is 9/2. Okay, please try this next one. Okay, always start by sketching the curves. And this is just a rough sketch, it doesn't have to be exact. So there's my parabola, y is equal to x squared. And this is the parabola, y is equal to 2x minus x squared. So the area I'm trying to find is this shaded region between these two curves. So this would be my representative rectangle. And first thing I need to do is find these 2 points of intersection by setting my two functions equal to each other. So that means I'm going to have x squared is equal to 2x minus x squared. Solving this, I end up that x is equal to 0 and x is equal to 1. So at x equals 0 and x equals 1 is where my shaded region begins and ends. So I have the integral from 0 to 1 of my top function, which is the red function, 2x minus x squared, minus my bottom function of my representative rectangle, which is the blue function, x squared. So again, we're going to start by simplifying. Combining my two terms, my -x squared minus my other x squared, I get 2x minus 2x squared dx. And now I'm going to find the integral of this and evaluate it from 0 to 1. Substituting in place of every x1, I end up with 1 minus 2/3, minus replacing every x with 0 is just 0 in this case. And so I end up with 1/3 as my answer. So the area between these two curves is 1/3. Okay, now we're going to look at finding the area of the region between curves that intersect more than 2 points. So we have multiple regions of intersecting area. This is going to be done very similar to how we've done intersecting equations. But this time you're going to have multiple areas. So let me show you by the example. So first I'm going to do a quick sketch of f of x, which is 3x cubed minus x squared minus 10x, which looks basically something like this. Okay, then I'm going to sketch g of x, which is -x squared plus 2x. So notice that when I do this, I have formed two areas between these two curves. I'll label this first area A1, area 1, and the second area, area 2. Now what we're going to do to find our total area between these two curves is we're going to find the area A1 and we're going to add area A2. To find area A1, remember that is just going to be our integral. But before we can integrate, we need to find our points in which these lines intersect. As always, to find the points where two functions intersect, you set the functions equal to 0 and solve. So these two functions intersect at x equals 0, x equals 2, and x equals negative 2. Notice that our first area goes from x equals negative 2 to x equals 0. So to set up finding A1's area, I would do the integral from negative 2 to 0 of, again, my representative rectangle. The top of my representative rectangle is the blue function. So that means I'm going to have the top function, which is 3x cubed minus x squared minus 10x, minus our bottom function of our representative rectangle, which is the red function, or negative x squared plus 2x. And then I'm going to add the integral of our area, or add the area of our A2. Area 2 begins at x equals 0 and goes to x equals 2, so I'm going to integral from 0 to 2. The top of this representative rectangle is the red graph, which is our quadratic. So our top function is going to be negative x squared plus 2x, minus the bottom of the representative rectangle is the blue graph, which is 3x cubed minus x squared minus 10x. And so now I'm just going to integrate these. So first let's combine like terms and simplify inside the integral. I'll do the same thing for the second area. Simplifying this, I get negative 3x cubed plus 12x dx. Now we're ready to integrate each side. So integrating the purple area, A1's area, I get 3/4 x to the fourth minus 6x evaluated from negative 2 to 0. Plug in 0 in place of every x gives me 0, replacing every x with negative 2. And I get that for area 1 is 12. And then doing the same thing for the area 2, or the green section, I also get 12. So notice that my drawing is not to scale, because those areas are not the same, but they actually are the same. So that definitely is not drawn to scale on most graphs, but it gives us enough information about what's going on. And then I have my total area of 24. Okay, when the graphs of a function y is a boundary of the region, it's often convenient to represent the rectangle using horizontal rectangles instead of the vertical rectangles that we've been doing. So we've been doing vertical representative rectangles. So notice all the representative rectangles we have up to now have been vertical, and remember our area was found by taking top minus the bottom. But now we're going to do horizontal representative rectangles, and so we're going to find our area by taking the right side minus the left side, the right function minus the left function. As long as these functions are written in terms of y, and we'll integrate in terms of y, so our integration will be with respect to dy instead of dx when we're doing horizontal representative rectangles. So basically in this section we've got two main formulas for finding area. If we're doing vertical representative rectangles, we'll do the area is equal to the integral of x1, x2 of the top curve minus the bottom curve with respect to dx. So the equations are written with respect to x. And now we have our second way of finding the area. We can also find the area from the integral from y1 to y2 of the right curve minus the left curve, the rightmost curve minus the left curve, with respect to dy. Okay, when we draw a representative rectangle here, it will be a horizontal rectangle. And our two equations, our right curve and left curve equations, will be in terms of the y variable. So x equals something in terms of y. So now you have to make a decision. Should I draw a horizontal rectangle or a vertical rectangle? And the easiest way to make the decision is from drawing your picture of what your area region looks like, and that'll help you make your decision. So I'm going to sketch this function. So on the curve of y equals 3 minus x squared is this red sideways parabola. And then x equals y plus 1 is this line. So the region which they intersect here would be this orange shaded region. Now notice I can't do a vertical representative rectangle, because at one point I would, if I drew a vertical, I'd have the red graph on top and the red graph on bottom, and then now I have a height of 0, so that makes absolutely no sense. So I have to draw a horizontal representative rectangle. So this is my horizontal representative rectangle. Now to solve problems like this, it's going to be the exact same way with the vertical representation of rectangle. First thing we got to do is find the points of these two graphs intersect by setting the two equations equal to each other. This time we're going to solve for y. And I get y is equal to -2 and y equals 1. So the bottom of this graph is at y equals -2. The highest point of the shaded region is at y equals 1. So to find this area, this orange shaded area, I'm going to find the integral from -2 to 1 of the rightmost equation, which is the red equation, or 3 minus y squared, minus the leftmost equation, which is the blue line, or y plus 1, with respect to dy. So again, we're going to clean this up by distributing the negative and then combining like terms. And we'll integrate integral of this function is -1/3 x cubed minus 1/2 y squared plus 2y, evaluated from -2 to 1. So replacing every y with 1 gives us -1/3 minus 1/2 plus 2. And replacing every y with -2, I get 8/3 minus 2 minus 4. Okay, finding a common denominator and simplifying this down. I'm just going to go ahead and find a common denominator for everything. So I'll rewrite this 6 as 36/6 and distributing the negative, so it makes it a positive term. And I have an area of 9/2. So the area between these two curves is 9/2 square units. All right, find the area bounded by these two graphs. Okay, first we're going to use our conics from college algebra to sketch these two functions. We know x equals 1 minus y squared has a parabola facing to the left with a vertex at that point 1, 0. And then the graph x equals y squared minus 1 has a parabola facing to the right with a vertex at -1, 0. And so our shaded region, our area that we're trying to find, is this area between those two curves. And so we are going to need to do a horizontal rectangle so that we have different equations on top and bottom, in this case left and right. So to find those 2 points of where those two lines intersect, we're going to set our two functions equal to each other and solve for y. I get y is equal to plus or minus 1. So the bottom of my shaded region is at y equals -1, and the top of my shaded region is y equals 1. So my area is going to be the integral from -1 to 1 of our right equation, which is the blue equation, 1 minus y squared, minus our left equation, which is the red equation, y squared minus 1. Simplifying this down and then finding its integral. I get our integral is equal to -2/3 y cubed plus 2y, evaluated from -1 to 1. Replacing every y with 1, I get -2/3 plus 2. And replacing every y with -1, I get 2/3 minus 2. Distributing the negative and combining our like terms and simplifying down, I end up with an area of 8/3. And that is how you find the area between two curves.